All right. So today we're going to hop back into forecasting and talk about another class of models for forecasting. And I'll talk about how we do our forecast evaluation. We're going to focus on the forecast package. It's really great for all of those things. That's going to be the first 45 minutes, take a 5-minute break, and then we'll jump into an introduction of state-space models. Okay, so today, Holt-Winters models and model evaluation. Hey, how about that? There we go. Okay. So we're going to be talking about two types of what's called exponential smoothing models. And this is a class of model where it's different than the ARMA models, where we are like explicitly depending on the previous time step or the previous few time steps. And that dependency can be kind of anything you want it to be. By that, I mean, like, if we were to write an ARP model, we could have P1 T-1 plus P2 T-2 ... And these things could be anything we wanted. So that dependency in the past is very flexible. In the exponential smoothing models, we are going to apply a certain type of weighting as an exponentially declining weighting. We're going to give more weight to recent observations and less weight to the past. We're not going to completely ignore the past, but we're going to give it less weight. Here is a really simple version of this. So this is a y hat. I don't know why the hat did not end up on top of the y. It's supposed to be on top of the y. So that's y hat. So that's our estimate of what we're going to observe in the next time step. And this looks, so this here is that there. So this is our estimate. This is just equal here. And if you look at that, it's like, wow, that looks kind of like an ARP model. It does, but these values aren't just anything. You can see they are exponentially declining, and it goes all the way back to the start of the time series. It just declines. And depending how much, or depending what the value of alpha is, tells us how much weight we're giving to past values. So if we make alpha equal to 1, then it's like an AR1 model. It only depends on the time step 1 previous. If we make alpha really, really small, then we're going to give a lot more weight to the past. In fact, if we make it 0, it's going to give equal weight to the past. And basically, our prediction of the future is just the mean of everything we've ever seen. Did you have a question? No. Okay. So that's your simple level. Just depends on the past. So we can add a little more to that and say, well, I'd like to also have a trend in there. What do I mean by trend? So a tendency to increase or a tendency to decrease. So if I look at some data and I see the time series is going like that, well, if I, kind of put my reasoning hat on, it's like, well, okay, like give me your best estimate. Well, I would say, okay, well, yeah, what I've seen recently, that should factor in. But also it's really obvious to me that it has a trend. It's going up. So I'm not going to ignore that and just like, if it's going up here, I wouldn't say, oh, my estimate's going to go like that. No, I'd say, I'm going to say whatever it was here, and then I'm going to estimate what that trend is and add that on too. And that's going to be my estimate. I'm going to factor in what that trend is. That's what's going on here. So this is my estimate for the next time step is the average level that I saw, giving more weight to the recent values, plus my estimate of whatever that trend is. And you think, okay, so I already talked about how you'd weight that, have this exponentially weighted average of past values to get your level. But what about that trend? Like how much it goes up each time step? Well, we could just say, well, it's just this, whatever I observed the last time step. Well, that's not really the best estimate. That's not what you're doing it with your eyes. If you looked at it, you wouldn't say, oh, let's just look at the last two. Actually, you're kind of in your head, you're doing that averaging of the trend, and you're picking something that's kind of the average of the most recent trends. And that's what exponentially weighted trend is doing here. So it looks like this. So we still have this exponential weighting of past values. Our trends pop in there, but the kind of the basic idea is the same, that we're weighting our observations of the past data, and that's falling off exponentially. And then for our trend, you can see our estimate of the trend is also weighting the more recent trends more heavily. So this is the one we saw between the last two time steps. This is the one that we saw a one-time step before. You see we're giving that a little less weighting, and this one's even further back. I didn't write it all out, but it would keep going. So it's this idea that we're estimating what the trend is. We're going to put more weight on the recent values, but we're not completely going to ignore the past. This is called the Holt model. It's very famous in forecasting. Holt-Winters model adds in a seasonal component. What we're going to do, we're going to estimate what that level is. It's going to be exponentially weighted. Same with the trend. Okay, so that part's it hasn't changed. What we add here is the seasonal effect. So what we're adding in is an estimate of, let's say this is monthly data. Do Januaries tend to be colder than the average? So if we were looking at temperature in the northern hemisphere, we would say yes, Januaries tend to be colder and Julys tend to be hotter. But how much colder Januaries are and how much hotter Julys are, that could have been changing over time, right? It might have been really different in the 1800s than it is now. And what this does is it also does exponential smoothing on that. So it estimates how much colder was last January than the mean I would have expected. So I'm gonna make an expectation of what this mean, what it would have been, and then I'm gonna look, hey, it was January. How much colder was it? Okay, so that's my estimate of how much colder Januaries are than what I would expect. And then I look at the previous January and say, well, how much colder was that one? Okay, I'm going to use a little information there. And then I'll go the previous one. How much colder was that one? So I use that information about how much colder Januaries are than the average to help me compute a seasonal weight. So how much colder are Januaries? Same thing for all the other months. So it's a pretty simple idea. I'm not showing a lot of math because just having the concept is enough. Well, again, I just said I wasn't going to show the math, but there's the math. But the idea here is that this weighting, you can see these terms are going down. And this is the seasonal weights. This is how much this January was three Januaries ago. How much was it different than what we would have expected? All right, so fitting these, how do we do this? So we're going to use the forecast package, and the forecast package has this function Holt, and then this function HW, which stands for Holt-Winters. You basically pass in the data, and it'll give you the fit. Simple, it's fitting those the models that I just described. You can also fit them like this. They are a subclass of the exponential smoothing model. In the forecast package, ETS is the function that fits that. And model AAN is a Holt model. The terminology for ETS is the first one has to do with the errors. The second one has to do with the trend. And this one has to do with the season. So this is saying, A is additive errors, and then M would be multiplicative. So this would be additive errors, and then a additive trend and no season. And this one is all additive, and but we also add the additive errors in this season. I'm just going to be focusing on these two types of Holt and Holt-Winters models. The multiplicative type, I'll show you how you can let ETS select the right model. A multiplicative type might come up like in the lab if your data are doing, let's say you have a seasonal pattern that looks like this. So let me draw it. Here is this. It's not that the seasonal cycle is changing over time. It's that the seasonal cycle is changing as the mean level changes. So this is YT. When YT is small, the seasonal cycle is small. As YT gets larger, if it were to go down, it would get small again. Like that. When does this happen? It happens when the errors tend to be percent errors rather than absolute errors. So if you say that the fluctuations, they tend to be like 10% higher or 10% lower versus being 10 animals higher, 10 animals lower, no matter whether you're looking at 1 million things or you're looking at 10 things. And there are lots of, as you can imagine, there are lots of situations where percent errors make more sense than absolute errors. The nice thing with the forecast package is if you're fitting your exponential smoothing model, you can use Z, which says, hey, tell me what you think this is. And it will tell you which model it thinks it is. And if it looks like it's a multiplicative model is better, it'll put an M here rather than an A. All right, so how do we fit this? It nicely, the forecast model makes this really simple. On the website, when you go to the lecture, you can download the R Markdown version of all our lectures. And I encourage you to do that for the lab, because it's going to give you, or I guess you can just copy the code too, however you want, but you can download the R Markdown if you want. So I'm going to be showing, like last week, data from the Greek landings model. Says, among other species, it has anchovy. And so here I'm going to load that in. And then in this next step, I'm going to take the species anchovy. I'm going to look at data before and equal to 1997. And then I want to get the log metric tons. So this line of code gave me a vector of log metric tons. The forecast package needs that to be a time series. Can't just be a vector. Needs to be a time series. So we pass it to this vector to the time series, and we tell it to what the start year is. So starting in 1969. Notice it doesn't have frequency there. So because it doesn't have frequency, what it's saying is that these data are not seasonal. So they don't have a natural season to them, like monthly, quarterly, something like that. We'll see how to specify the seasonality if the data are seasonal. If you want to have forecast test for seasonality, you have to put in the frequency. And it would have to be something other than 1. So it wouldn't make any sense if it were 1. If it's 1, it's non-seasonal data. All right, so we set up our time series, and then if we fit the Holt model, it looks like this. So here, I made this into a time series. So that is a time series, so boom. And that's it. It fits that model. So the Holt model is the one where the mean level is changing, and it's going to estimate the mean level by the average of recent values. And then it's also going to have this trend. It's going to estimate the trend, so how much it's tending to go up or down. It's also going to be a weighted estimate from the past. And then I can forecast. So let's check this out. Right. So there you go. And so this estimate right here, it's the this one is going this trend here, which was kind of high. That one's going to affect it the most. That one's going to affect it a little less, and then that one even less, and that one even less. And then when you get way back here, this trend back here, that change, that's not gonna, it's too far back. That's not gonna have any impact, because how much influence past trends have in this estimate of this, it's going to fall off exponentially. So it's going to weight these recent values more. The really nice thing about the Holt method is that it will evolve over time. So if this thing then starts to turn downwards, this estimate of the trend is going to start to turn downwards. It's going to naturally evolve over time. It's also naturally, it's kind of putting this sort of mean level here, and that estimate is going to evolve over time. So it's not like going to use like the average of everything, and it's not just going to use the last value. It's going to be kind of the average of what it's seen over the recent past. All right. Yeah.
When you're fitting these models, is it making any assumptions about like a distribution, or it's just like fitting, taking these averages?
Yeah, it's basically just taking these averages. Yes, when the estimation method, it is easier to estimate these models if you make those assumptions. And so that's the classic way to estimate it. You'll put it in what's called a state space form, and you make assumptions about the distribution of those errors. But like, you can fit these models in like an Excel using. Yeah, that's a good question. So that is coming from that state space models. So that is coming from the assumed this particular normal error distribution. Yeah. Yeah, good point.
You don't need that just to get forecast.
Correct. And the classic one would not have like the classic way that people would estimate the Holt model, it would just be a point estimate. This model wins lots of forecasting competitions. Super simple. It's actually, like I said, you can like create an Excel sheet, and it's just a series of algebraic computations to, well, you do have to do, there's one part here, these alphas. So you do need to estimate the alphas and the betas, and they will use a optimization algorithm to minimize the forecast errors, which we'll talk about forecast errors in just a second. All right. Any other questions about these? Yeah, go ahead. Yeah.
What's the last code, which is like H?
Yeah. So this is number of time steps into the future that you're going to forecast. So if you look here, this is kind of eyeball it. It's 1, 2, 3, 4, 5.
I'm curious, like, does the code will output a formula, for example, like let's know like what's alpha, what's beta?
Yeah. So if you were to do print fit, it would output what the estimated alpha was. Yeah. You can also do, so instead of plotting a forecast, I could print forecast and it would show me what these estimates are, and it also would give me the numbers for these bands. All right. Okay. So validation. So we want, in general, we want to evaluate the performance of our model and of our forecast. And the way we do that, and this isn't specific to these class of models, it's kind of any of them, when we're evaluating our forecast, we're going to take our data and we're going to subset it into a part we're going to use for training and a part we're going to use for testing. So in this case, I'm going to use all the data before 1997 to train it, and then I'm going to test it on 2 years. So it's not a lot of testing data, but the time series is not super long, so I'm a little limited. So I'm just going to test it on 2 years. And so now I'm going to take the data. So I've subsetted here, subsetted those landings by year, and I'm going to pick the species, which I said is anchovy, and then I'm going to take the log metric tons. So now I have a vector of values. This is that training data. So I'm going to train on all the circles, and I'm going to test against the triangles. Key point, we need to hold that test data out and not look at it for fitting. So let's do this first with a AutoArima. Again, it doesn't what I'm talking about is not specific to a class of models. It's general for testing forecasts. So we're going to fit, in this case, going to fit an auto ARIMA to the training data. So that fit ARIMA, there we go. And then we're going to get a forecast. So we take that, put it into the forecast, and we're going to do H equals 2 because I held out 2 years of test data. So that's why that H is equal to 2. It's equal to the number of years of test data I have. So let's plot it. That's what it looks like. And we can add our points to it. And you can now see that this is the forecast errors. So that there, the difference there is that forecast error, and then that one is that forecast error. So, simple idea. How do we quantify how big this is? And there are lots of ways that we will quantify how big that is. So one is just the mean error. Let me go back here. What is this? So the FR error, forecast error, I'm taking the test data and I'm subtracting the estimates, which are in mean of the data frame FR that comes out of that. Okay, FR is a data frame, and it's probably a tibble, honestly, but it's a data frame basically. And the mean is our forecast. So we're going to subtract that from our observation, and those are our errors. So mean error, there we go, just take the mean. That's not actually used much. That would be how biased your estimates are. So like, why wouldn't you use the mean? Well, imagine like if one error is like up here and then the other error is way down there. So one is like negative 100 and the other is positive 100. We took the mean, we'd say, whoo, we got it. The error is 0. But it would tell us how biased our estimates are. Much more common, this is the one you're going to see all the time, is root mean squared error. You take those errors, take the square, take the mean of the square, and then you square root it. Super, super common. Mean absolute error, you also see that. That's called MAE. Mean percent error, see that all that much. But sometimes that, especially like if you're looking at a multiplicative model, these percent errors would be the thing that you would look at. The if you're working with output from a forecast function, you have this nice accuracy function, and it works like this. You give it the forecast object. It needs to be the same length as your test data. So that's, remember I had H equals 2, so it's the same length. And I compare it to my test data, and it is going to give me this. So the first thing that it shows is the training set. That is the error, like how well it's fitting the actual training data. And then this is for the test set. So it computes all those for you. It's really nice, makes it super fast. Okay. Yeah.
Somebody saw from like that model is good, model is not good.
Smaller's better.
Maybe like when you see the comparison between the training set and tested set, you're seeing like the tested set would be close to training set.
No, you would be, you're using this to compare models. But I guess what I would, you might look at this and say, you know, I mean, well, I guess, I don't know, it seems kind of obvious to me that your forecast are going to have larger errors than the errors within the data that you train to. Because you're fitting to the data, so like hopefully your errors would be smaller, you've just fit to the data. But now you're forecasting to new data, and you can see that those errors for your forecast are much larger. It's only 2 data points though, so take that how you will. Yeah, one like general comment is that when we're comparing models with AIC, we are essentially looking at the training errors metaphorically. So we're looking at how well it's fitting our training data. We are not asking how well does it predict new data. Theoretically, yes. If we kind of according to like large sample theory, the AIC should be correlated with out of sample forecast. It's approximate, it's a large sample approximation. In general, I have found that my performance on out of sample data can be very different than what I would get from looking just at AIC. Yeah.
Would you ever like pull out some data from the middle of the time series for validation, or are you always forecasting?
Well,
Yeah.
I'll just, what is your intent? Is your intent to do forecasting? Are you trying to evaluate this, the ability to forecast models? And if so, then I would always test it in a true forecasting sense.
Yeah. Yeah, you're
see when Eli starts talking about stage-based models, right? You could fit that model, and depending on what values you took, you could actually have the thing doing sort of a forecast. That would be one option, and another where it actually considered today's observation. Another way, it got all the way to the end and then worked its way backwards. So you could, some of those would be a bit of a cheat.
Yeah.
Context. So I think what you actually proposed here is that most folks are the right for.
Yeah, for a forecast. Yeah. Yeah. So I was pausing because there are absolutely situations where you would do leave out in the middle. And that is when you are testing the performance of interpolation. So the goal is to fill in missing data. You're using you would not use this class of model to fill in missing data, but the models that I'm going to start to introduce at the end of today, absolutely use those a lot for interpolation. And in that case, yeah, that's what you do. All right, so, okay, so now you've seen how to test the accuracy of one model. Now, how do we put this all together and compare a candidate set of model? This is what you're going to be doing in the lab. You're going to be comparing candidate types of models and looking at how well they make forecasts of salmon. You write a lot of code, you kind of go about it methodically. So this would be a ARIMA model, and I'm not going to use auto ARIMA because I want to tell it, hey, I want you to test this particular model. This happens to be the one that was picked by auto ARIMA, so I give it the order. And then I put in here and said, hey, I want to test it against an alternate model too. Here's my alternate one. And so these are the tests from accuracy. So I fit it, forecast it, then stick it in here, testing it against the same data. Same thing for this one. And then going to also do the Holt. and then you can show a summary. And what you see, this is just the forecast errors. Keep in mind, I just had 2 data points. But for those 2 data points, the Holt had a bigger root mean squared error. Wow, this is all jammed up together. Here are the values here. So you can see the best Auto-Arima has a lower error, root mean squared error. So that's going to be the general approach you will take for testing the performance of a set of models. Okay, so 2 data points for testing, not that great. You're not going to put a whole lot of stock into how well it did for just 2 points. So what do people do when they need to test the model and they don't have like tons and tons of data? What they do is they do something called cross-validation. And that means chopping the data set up into these smaller amounts and creating a whole bunch of forecasts. Here's the sliding window approach. So the first forecast, we take 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Okay, so we take these points and then we forecast this next point here. Then the next one, we add 1 data point, we forecast that one. We do that, and we do the next one. So that we create now 9 forecasts from our data. As you might imagine, you do this when you are constrained by the amount of data that you have, because these forecasts are not independent of each other. Notice that these 2 are almost using the same training data. They're not independent forecasts, but your hands are kind of tied because you don't have a ton of data. You're doing the best you can. Another approach. I should also say the other problem with a sliding window is that the amount of data that you're using to train keeps changing. So you're kind of it's not really apples and oranges. They're all oranges, but they are a little bit different oranges, right? You know, this is maybe a navel orange and this is maybe a tangerine, right? They're still oranges, but this one has a lot more data. So yeah. So the fixed window approach is a better approach. Here, we're always using 10 years of data to train, and we're testing 1. But we're going to take our full data set, which is going kind of up to here, and we're going to have this sliding window of 10 years here. Now, still, they're not independent forecasts because these 2 training sets overlap quite a bit. Like this one is that right there. So again, they're not independent forecasts. If you had enough data, you would push that window, the separation between the windows, as far out as you could. Depends how much data you have. So ideally you would like to do is have 2 independent forecasts. But if I did that, I would only have 2 forecasts. So then if well, I can't really evaluate my forecast with only 2 forecasts. I need more. And so you'll kind of, I mean, realistically, what you do is you see what the reviewers will accept. Well, they kind of go for it, you know, that much overlap, they may be like, no, need a little bit less. Okay. The forecast package has a nice little function that's going to do this for you. It's going to do these sliding windows for you. Question mark TSCV if you want to try it out. You don't need to do this in the lab unless you want to. If you're curious about cross-validation, I definitely encourage you to play with it because it's a nice function. We do want you to work with the accuracy function, though. We want you to be evaluating forecast. Okay, so let me give you a kind of a orientation of the TS function because it is a little weird in case you want to try this out. So the TSV function, time series cross-validation, it takes your training data and then it takes, let's see, where is this? I guess it's using the default here. Okay, that is too bad. Okay, so it is using some default for your window size. And I should have put that information here. So it's using like all your training data, and then it's going to chop this up for you. And there's some default that, like I said, it's using for your either your window size or the amount of they're called folds, an amount of kind of blocks it chops the data into. So it's going to do that. Then you need to give it a function that returns a forecast. So this is the thing you have to create for it. So here I've created this function, and what it does is it takes X, it takes some data, it has to look like that, X, and I tell it what kind of forecast I want to do. So here I'm going to fit an ARIMA model. It's going to take some data, and I'm going to give it that kind of order, and I'm going to make a forecast that far into the future. Here's my function, and then I tell it how far into the future. Here I'm going to say 1, I'm just making 1 step ahead forecast, and I'm going to give it this class of model. So first difference is autocorrelated error. And what it gives you is a bunch of forecast errors from these cross validations. So it runs this thing for you. It gets you a forecast, and then it compares with what the black point actually was there, and it's going to give you those differences. That's what it outputs for you. See if I have another example here. Okay, that's kind of the same, but I'm comparing forecasts that are 4 years out. This is actually kind of interesting. So you can compare how the accuracy of your forecast breaks down as you try to forecast farther and farther out. So here, what I did is I did I show the code? Oh yeah, here's the code. Okay, so when I gave it that H, instead of giving H1, I said, hey, look 4 steps out. So it's doing that right here. It's looking at a farther forecast. And as you can imagine, those forecasts are going to have more errors. All right. So if you want to try this in the lab, I encourage you to do that. You know, play around with this code that I'm giving you in this lecture and just kind of experiment with it. Do $TSV. It'll give you the background on the function. I didn't throw this into ChatGPT, so I don't know if ChatGPT knows it. I bet it does, though, because forecast has been around for a while. All right, so this is a comparison of the 1 ahead and the 4 ahead. This uses a sliding window versus a fixed window, but let's just compare these. You can see how this root mean squared error goes up 0.38 if we're doing 4 steps ahead versus 0.22 if it's only 1 step ahead. Okay, so summary, forecast performance. All right. So when we want to test the forecast for performance, we're going to separate our data into a training set and a test set. Okay, first step. And then we do forecasts that are the same length as our test data, and we use the accuracy function, and it will spit out these forecast errors, and those forecast errors appear in the line that says test set. Repeat this for all the models that you're testing. So pretty simple. Okay, let's go through that. I'm not going to do that. Okay, so now we are going to talk about the Holt-Winters. The Holt-Winters is the one that has that seasonal effect, and we allow the seasonal effect to evolve over time. I'm going to do this with the Chinook data set in the ATSA library. And this is the one that you are working with in the lab. It looks like that. It's just monthly data for different states. Hopefully you've already played around with it. When we are going to put this into the forecast package, we need to make it into a time series. So first thing, I'm going to take the data set, Chinook month, and I'm going to get the state of Washington. DF is just the Chinook in Washington. And now I'm going to make it into a time series. And I need to give it the vector. So I'm looking at log metric tons. I can't give it the data frame. I need to give it a vector there. I'm going to tell it when it starts. But now, because this is monthly data, I don't just give it year. I also need to tell it what month. Like it didn't have to start in January, right? Could have started in June. So this is the year, 1991, first month, that's January. So if it's June, if it started in June, it would be a 6. So I have to give it 2 values. And then frequency is the seasonality. If it's monthly, it's 12. If it's quarterly, 4. So that's the setup that you're going to need to do. Let's plot it. Once it's a time series, then it's like really easy to plot things. It knows and takes care of the time for you. So there you go, lots of data. So let's fit the Holt-Winters to that. I'm going to take 10 years of data, 1990 to 1999. And I'm going to use the window function. It's not part of forecast, it's just a standard time series function. And how that works is you give it your time series, you tell it when do I start and when do I finish. Seasonal data, so I need to tell it the year and the month, so 10 years. And now I fit it. Holt-Winters, just like that, HW, give it the data. That's it. And it fits that model for me. And then I can plot it. H is 24. I'm forecasting 24 months. And there we go. There's the forecast. And you can see how they compare. Okay. And the cool thing is if that seasonal effect is changing over time, then so like if this is tending to get bigger, so imagine like there's kind of a mean here. If this is getting bigger, my forecasts are going to be bigger. And then if this starts to get smaller for whatever reason, my forecasts are going to start to get smaller. So it's going to evolve over time. Compared to a seasonal ARIMA, the Holt-Winters tends to beat a seasonal ARIMA. A seasonal ARIMA can't evolve. So like in the forecast competitions, ARIMAs, they win in certain types of situations, but like in a lot of real data, they're not going to win because they can't evolve over time. Right, so let's see what this looks like with auto ARIMA. Why did I have to do that? Oh, I know, it's a relic from something. Okay. Okay, so I put in this no miss data. Actually, what I'm doing there is I'm just making sure I'm fitting the auto ARIMA to exactly the same data that I just fit the Holt-Winter to. So instead of like giving this right here, the training data, I am going to take the fit here, that fit there. And if you look at the X value of that, it is the value that it actually fit to. Why would that be different? Because in Holt-Winters, it can't take missing values. This is a big problem with Holt-Winters. It's an unfortunate feature. You have to interpolate because if you have any missing values, it's going to like chop it down to the longest segment. Right. So I'm just sort of making sure that I don't make a mistake and fit to different data. So I grab the data coming out of that Holt-Winters fit. And then it works the same, use that auto ARIMA, boom, plot the forecast. And this is the forecast for the auto ARIMA. And it looks like, it's doing a little better, but actually my y-axis is a little different. We can evaluate the forecast and where is this one? Which one is this? Forecast. Okay, so forecast is I'm fitting the Holt-Winters. So those are the forecast errors for the Holt-Winters. And then I can do the same with the ARIMA model. And let's compare. So that's 0.9 versus, oh, come on, where is it? 0.85. So a little bit, and it's still, yeah, it's 12. Yeah. So it's a little bit better for the Holt-Winters there. So you see that's 0.85 versus what I got with the best fit ARIMA model there. All right. Okay, so that is the end of that class of model. Let's take 5 minutes. And so get up, walk around a little, and we're going to do an introduction to the next class of model. This will just be a real like high level introduction. We're going to get into the meat of it actually over the next 4 lectures. Righty. All right, so we're going to finish up with getting into the class of model called state space models. This class is extremely important in time series analysis. It is used across many different fields. And so, when we think about a univariate time series, so we just have one time series, and these are the points that we have through time. And we can, think about that there's some mean level that is going through the data. And a core difference in the models that we have talked about so far in the state space models is how we think about this level here. And like whether we're interested in it, but also how we might estimate it. So what do I have here? Okay. Do I have? See, did I put that there? Yeah. All right. So in the classic ARMA model, the approach to that black line is, I do not like that. It is, I need to get rid of it. I am going to difference that data until I annihilate that black line there. and then I get myself to something that is stationary. I don't care how much I've transformed the data because I do not care about that black line. I am trying to model these errors, and I am trying to create a forecast. So I want to model those errors so I can use the best way possible, use all the information in the data to take this point, maybe a few other points and make a forecast. And this black line is just muddying things because all I care about is the error. So I'm going to just like get rid of it. I'm going to difference it till it goes away. The models I was talking about this morning, your exponential smoothing models, we're going to compute essentially that mean by using some additive sums of the past observation. But it's not our goal to get this black line. That's not the goal. The goal is to find the best value of this black line right here so that I can make a forecast forward. So my goal is to get the best value to start with. And it's not this one, that's going to be too low. Something else, and I'm going to figure out like the best weighting of the past to find kind of my starting value for my forecast. So it's not my goal to get that black line. What we are talking about now is state space models, and we care a lot about that black line. In fact, that black line is often our goal. We are trying to get that black line because that black line has information in it that we want. So I'll give you just kind of one example. Like, what if those X's are locations of an animal we are tracking in space, and we want to know where that animal was, because we are going to look at correlations between what it was doing in different locations and say something about how animals use their habitat. So we need the black line to ask that question. We care about the black line. We're not trying to predict where the animal is going to go next. We're not interested in that. The animal is long gone. We took the transmitter off it. We want to know where it was. And also, the animal might have gone missing for a while, like the tracker stopped working. So we might have these gaps in time where we don't have any data. It's really important for us to get an estimate of where was the animal when we weren't seeing it. So the class of models we're going to be looking at are getting at that. The class of models that we are going to be working with, they are typically going to be modeling that black line with a random walk, and often a non-stationary random walk. That means we are not saying that the random walk, that is the animal, that it keeps returning to the same mean level or returning to the same place. It's not doing anything like that. It's just we allow it to wander off and visit anywhere out in the environment. We don't have to make that assumption, but what you're going to be seeing, we're typically going to make that assumption. Right. So as I said, we're going to be talking about this class of models a lot. Next week, not next week, on Thursday, I'll talk about the multivariate version. And then we'll have 2 lectures on those. It's a pretty sort of big amount of content. And then we'll have, I think, Mark, are you next? Are you doing the DFA? Is it DFA and DLM?
The DFA is
25th. Okay. So yeah, then we'll have a lecture on dynamic factor analysis, which is kind of like PCA for time series. And then dynamic linear models, which is a model where it's like a linear regression, but the weights in your linear regression are going to be varying over time. So you might say, like, what is the effective temperature? Well, if you did a linear regression, that would be a constant term, but in a dynamic linear model, you would allow that weight, the effective temperature, to evolve over time. Okay. So another feature of the state space approach is that you treat the data as the data separate from this underlying random walk. So you're going to have an observation process and then a state process. Let's see some examples. So here's the univariate state space model. It's the classic case. This is a random walk with drift. Memorize the form of that. You're going to see that a lot, not just in this class. It is, random walks are extremely important. And so there's no term here. It's just this is a function of the past. And then here I have a drift term, so it can tend to go up or tend to go down. And in the classic random walk, this is white noise. We are going to be treating this as white noise for 90% of the class. Towards the end of the class, we'll show you how to have other types of noise if you needed that. However, white noise comes up when if you add together a lot of non-normal noises, you'll get something that looks like white noise. And so in real data, in nature, we often see white noise because the noise that we see in the thing we are measuring, it is something that is impacted by all kinds of different noise. And that noise can be adding together. And so because you get these kind of additive noises, things often look kind of bellish shaped. So it's not actually a terrible assumption in many cases. In some cases, it's a terrible assumption, and then you want to use something else. Okay, so that top one is the X is the hidden state. Going forward, we will always call the hidden states the X's. We don't see those directly. What we see are the Y's. We see this, and the Y is observing the X's. This is a very, very simple observation model. In this one, the Y is observing the hidden state, the X, directly. It's just equal to X plus some noise. This is the last day. It's going to look really simple. Okay. So, like I said, super, super important class of models. These are some of the really classic books in this class. Mark and I have both lived in these books for a lot of time. Spent a lot of time in those. These are also some other really classic classic autoregressive processes that we'll see in this class of model. This is the one I just showed you. This is a random walk with drift. Goes up and down. This is a pure random walk. You'll notice this one has t+1 and t doesn't matter. This is also a random walk. I did it that way on purpose, just so that you don't feel like you always have to have the t there. The point is that these are one time step apart. This one does not have drift. And so if somebody says a random walk, they're usually talking about this. And random walk with drift would be that one. This would be your AR1 process. If this is between -1 and 1, mean reverting. This is going to lift it up or lift it down. We will not add a trend because that's there. You will always have mean reversion around a level like that. Okay, We are going to be doing these mainly. We'll talk about this towards the latter half of the class. As I mentioned, random walks come up a lot they come up a lot in science, but they come up a lot in ecological data and, nature, movement, changes in gene frequency, somatic growth, population size. Those kind of things are classically random walks. Multiplicative random walks. So this would be your population growth. So that happens because growth will tend to be a percentage. So you might say that the population grows by 10% per year, something like that. And when we're working with population data, we take the log and then we get back to these linear additive models. So you're going to see us taking the log of data a lot. And that log is happening where we think the underlying process is something multiplicative. So we think the errors are percent errors per year. Okay, Gompertz model. I'm not going to go into this. We're going to talk about this later. This has to do with how we model density dependence in this class. So we'll do it with this kind of simple version. Here we go. Yeah, so that model there can create things that look like this, We're going to play with some data from, well, we may play with the Lake Washington plankton data. Kind of depends what we decide to do in the lab. We've played with that data a lot, and if you look at that data, it looks a lot like these. And the Gompertz model is one way people have analyzed that. All right, so that model looks like super simple. It is super simple. In fact, this model here has, well, I mean, technically it has two parameters. It has this drift term, and then it has this variance term. Okay, so it just has two. And so if we just set these to these values right here, and I simulated 6 of these, and you can see that it can take a lot of different shapes. So very flexible. So definitely able to model that black line there. Okay, so I've talked about what state space means, and let's reiterate that. This is a really important point. So state space means we've got an observation process and a state process. So we have some process that defines how that black line is wiggling around. And then we have another process that defines how we observe that black line. This is a very simple version of just observing the black line. We're going to get more complicated. So let's look at some examples. Again, this is a very simple example. So here is the univariate example. I've got those. These are actually some real data, population counts of wild dogs. So this is what they counted out there. And then if we fit a state space model to this, we fit a random walk with drift. This was what we would estimate that random walk is. And then the difference here would be our errors. The model does not care about these X's. This is a great thing about having an observation model. We don't have to observe every data point. So in this class of model, missing data are fine. Always like putting, wow, it's kind of washed out. Well, it's even better that it's washed out, because this is a real example of when I was working on stellar sea lions, and we were putting together the when we were analyzing the survey data. And this was our survey data. This is one of our survey photographs. And yes, we would sit in a very dark room with a white paper on the wall and put little points as best we could, like, oh, is that, these are sea lions. Yeah, and that's how we would estimate them. And you can see there's a lot of error in there, potentially. I know there's a lot of error. And a really kind of interesting thing about fisheries and ecological analyses that's really different than, say, like financial data or engineering data or sensor data. So one thing that's different for us is that we typically do not know what the error structure, what the error amount is. We can't go out and like take our sensor and stick it in a known temperature bucket and take a whole lot of measurements and then come back and say, all right, this is what the error variance is. That's not something we could do because we're going out there and we're measuring fish, or in this case, you know, with the seals, not seals, sea lions, we're measuring them, we're flying over and we're taking pictures. And there's all kinds of things that make our estimates variable. Like animals respond to the environment, and they may become more cryptic or just not visible in different conditions. There are population factors that change how visible they are. There are species interactions. So, you know, if a whole bunch of killer whales came by that island right before we photographed, you know, a whole lot more of those sea lions would be out on the rocks and visible. So, you know, things like that. Or there's lots of different ways that species interaction causes all this variability. And then, so there's all that, so that's citability. And then we have sampling variability that is also affected by all these things. So this is kind of a classic problem for us, is we just don't have a way to estimate what that variance is. It's just unknowable. Okay, so here's our data. So how are we going to separate out what this process variance is versus observation variance? So here's our data. Let's go back here. Okay. Yep. Let's go here. Okay. So let's look at this state space model. So we fit this, and here is the X. This is that underlying thing. And the difference between this and this is our observation error. So our it's called non-process variability or observation variability. So as I said, it's the difference between this, the blue line, and our observation. That's going to be our observation errors. Okay, so that's simple. What about our process? Our process is the difference between what we expected the next time step to be. So now think about everything we've been doing the last 2 weeks with those AR models. You can make a forecast from the past into the future, right? So we make a forecast. So it's like our forecast errors, one step ahead forecast errors. That is our, what's called your process variability. Okay, so it's the variability in this blue line versus the variability, the difference between the blue line and the data. So how do we separate the two of these? This may seem like this is impossible. Like, how could you possibly separate those two variances? Well, they look really different. This is what error looks like. That is, if it's not autocorrelated error, so it's just random error. Look at that. Look, you can pick that out right with your eye. That's just like shaped like that. Versus this, you can, there's something looks kind of autoregressive about it. You can pick it out, and it is this difference between these shapes that allows us to separate the two. It's the difference between the temporal autocorrelation that allows us to separate the two. And actually, you can do pretty well at estimating these two variances. The way that we estimate these, how the way we get these is something called the Kalman filter and smoother. You don't need to know the math behind it, just need to know the basic, what it's for. And it is a algorithm that allows you to solve for the parameters in this. So it allows you to solve for that, and that. It's going to get those variances for you. Yeah.
I'm confused. Because you say the errors look different, but the WT and the BT look the same to the different letters.
Yeah, they do. Yeah. But that equation there, the y, the difference between the y, so that that forecast error is not that WT there. Not conditioned on all the data. That's yeah, it's like yeah, okay, how do I explain it? I think
Is it just like the difference from like X?
yeah, it's that you've got this autocorrelation here. So it's that this is the difference between these two. So if I were to show you xt minus 1, it would look like that. But that's not what we're fitting to. We're fitting to that smoothed X line. And if I looked at the differences of the Y's, it would not. So if I take this difference, normal. If I took these differences, YT minus 1, it would not look like that. Would not be a normal. It's going to, yeah, I mean, you can play around with this simulation. Yeah.
But it's because you have X minus 1.
Correct, because you have the X minus 1. If you didn't have the X minus 1 there, you wouldn't be able to separate them. Yeah, no, you have to have the X minus 1.
So you're like looking at those different plots, does the one for X have like the X T minus 1 that's like in that error term?
Yes, it is a conditional error. Yes, it is. This is the forecasted value conditioned on everything you've seen here. It's conditioned on all this data. That is your forecast. And so this is what's called, yeah, a conditional forecast error. See if I can, yeah. I don't know. I've never thought of a way, just kind of like an intuitive way to explain that, and I'm failing again today. Okay. Let's see. Oh, we're basically done. Okay, we're gonna do that. Yep, I'm gonna stop there. And then next week we'll talk a little, I'll finish the lecture today. I just have a few slides to talk about diagnostics. And then we'll start getting into multivariate stuff. Yep.